we know that cliques minimize the surplus, but cliques are very far away from triangle tree. So because we sort of have to deviate away from them, now random graphs might not be a bad example, but random graphs contain triangles very at very small densities, so they are bad as well. But actually the most natural thing to look at is so-called optimally pseudo-random triangle tree graphs. But what is a pseudo-random graph? A pseudo-random graph is a graph where both lambda 2 and lambda n grow roughly like square root of d. I don't really care how as long as some sort of a reasonable constant that's going to be good enough for applications, because we care about only multiple constants. For our purposes, let's call optimally pseudo-random graphs as these guys. And obviously we want these to be irregular as well. Here we can be a little bit flexible and say that they are roughly the irregular, meaning that the degree sequences don't deviate too much from the average degree. For simplicity and for intuition, just assume that they are regular. Okay. So I believe something I didn't have time to discuss on previous days, but which is important. So if I take a subset U, then the discrepancy, so the number of edges in U minus the edge density, average number of edges we expect to see there, is upper bounded by roughly lambda times U times U, and then we have to add most of the error term. And similarly, it's lower bounded by lambda n over 2. Remember that this is a negative term, because lambda n is always negative, minus d. And the proof is very similar to the proof of the expander mixing lemma, although here you don't get the absolute values, because you are basically applying to the same vector twice, so you get sum of alpha I squares, so you don't actually have to apply Cauchy-Schwarz, because you like to calculate just simplify it a lot. So in particular, this has a nice conclusion of the corollary that positive discrepancy of G is upper bounded by lambda 2 or like B over here, and the negative discrepancy is upper bounded by lambda n plus n. And again, we should think of these as something we don't care about, but we just have to add there to sort of avoid trivial obstacles coming. Like, for example, we need something else than lambda 2 over 2 times n on the right hand side because of the wrong graphs, because they have lambda 2 equals 0. So that's why we add this d term, which should be treated as sort of usually a smaller order term. Moral of the story: the eigenvalues control positive and negative discrepancies. Similarly, the surplus, which we know for the irregular graphs is of the order negative discrepancy, is controlled by lambda n. So lambda n being small in absolute value means, for the irregular graphs, means the surplus cannot be too large. There are also reverse inequalities connecting these to so-called energy of the graph, which is the sum of the absolute values of the eigenvalues. For pseudo-random graphs, the energy is going to be, because a lot of eigenvalues are actually root d, of the order root d. So you can sort of think that for pseudo-random graphs, this is tight. So the surplus is actually roughly lambda n times root d. So they got, in that sense, behave like random graphs, because for random graphs, the surplus would be also and that sort of thing. So for optimally pseudo-random graphs, surplus is going to be of the order and that sort of thing. This is not supposed to be sort of a rigorous argument yet. Just the intuition varies. How do we actually come up with a good guess on the actual exponent?
What is the reason behind the last? The last step, like why?
Here.
Yeah.
Because for the irregular graphs, the surplus and the negative discrepancy are within constant factors of each other's by one of the exercises that was given, I think, on Tuesday. Here. And I think here I want also the graph not to be incredibly dense to avoid near clicks. But that's sort of the stupid regime anyway, which we don't care about. Okay, so the number of edges is of the order d times n. But there is no relation between these two guys. But another thing is that optimally pseudo-random graphs can't exist for all the densities. So there turns out to be a very natural upper bound, which comes from the fact that, recall, I believe on the very first lecture, one of the exercises was to prove that the sum of the cubes of the eigenvalues is 0 when G is triangle free. Because that's basically, this expression is counting the trace of A cubed, and the trace of A cubed is just a number of triangles because it's the sum of Aij, Ajk, Aki, which is counting. That is the indicator function of the event, is do I, J, and K form a triangle. Okay, so this, on the other hand, is because G is irregular, so the first term is D cubed, and all the others are at least minus are at least lambda n cubed. Basically, okay, I could add n minus 1 here, because like the very extreme scenario would be that every other eigenvalue is lambda n. In reality, because we are working up to multiplicative constants, it will be roughly true that the linear number of them are up to multiplicative constants minus root d in the optimal pseudo-random regime, but this is actually not too bad estimate if we ignore multiplicative constants. So we get that lambda n is upper bounded by this expression. But we know that this should be roughly root d. So we conclude, okay, maybe an easier way is to already plug in over here root d. So we conclude that d to 3 should be roughly n times d to the 3 halves. So d should be and this is actually inequality going this way, because no.
The lambda n inequality goes the wrong way, right?
Sorry?
The rightmost inequality. The next one.
Oh yes, you're right. This should be greater. So yes. No, this one is right. Yes, so D should be less than n to 2/3, so that's good. So in particular, the average degree is going to be, or the regularity can't be too large. And now, if you try to maximize n times root d in terms of nd subject to this condition, it's not too hard to see that the maximum occurs when you choose E to be this guy, in which case n times root d is just n to the 4/3, which is nd to the 4/5. So we get our exponent 4/5. So Alon actually proved that there's an infinite family of optimal pseudo-random graphs of this density. Right? Every one of these graphs is D regular for D roughly of the correct magnitude, and lambda 2, lambda n are both of the order root D. So this implies that each of these have surplus. Okay, let me at most m to the 4/5 by this by this type of expanded mixing lemma argument, because the surplus is also upper bounded by n times lambda n, which gives you exactly this, which might have been one of the exercises. But anyway, that's usually it. So 4/5 is the best possible exponent one can ever hope for, and now our aim is to prove by using Goemans Williamson method that actually this is also achieved for every chief.
Want a big omega or big O?
So far, I haven't proved that it's a lower bound, but by this spectral by expanding mixing. So what I'm saying is that Alon proved that optimal pseudo-random cross exists for these parameters, and for spectral reasons we know that the surplus is at most at n 4/5. We don't yet know that it's at least, but we are now going to prove that for every graph it's going to be at least n to 4/5. So then it also holds that this is actually tight. But here I'm just sort of showing an example, assuming that like this Alon's construction exists, which it does, then this proves that 4/5 is actually the best possible exponent. and kind of gives the problem
But in the theorem statement, you don't need the triangle free, right?
yes, sorry. And Gn is triangle free. So what I'm saying here is that there is an infinite family of graphs which are triangle free and for which the exponent 405 is cannot be improved. I'm not saying anything about the lower bound yet. The lower bound will come next. But this is just an example showing that 405, if it can be attained, then it cannot be improved in general.
Sorry, so it's upper bound for triangle free graph, but not for any H.
It's an upper bound for this particular family.
Oh. Okay.
Not in general, because like bipartite graphs have obviously very large circles. But this, so basically, all this is showing cannot be replaced with better one.
Oh yeah, okay. I think my question is, if you replace triangle with other kind of fixed graphs, then
Okay.
what will you?
Sorry, for example, for KT.
Yeah.
I believe that already for so for K3, it's not known whether optimal pseudo
for
exists.
K4, you don't know.
So there are like basically the 3/4 in the Alon Walvas-Krivilevich-Shudakov conjecture is kind of motivated by a conjecture that optimal pseudo-random for KD3 graphs exists, and you for KT you can also come up with an inequality for between D and N, which gives you some upper bound on how large D can be in function of N and T if your graph is optimal pseudo-random for KT3. But yes, for even for K4 graphs, it's not known, and that would have given a proof of the Ramsey number between 4 and T, like up to the correct exponent.
Yeah.
But I mean, they found a graph which sort of circumvented this optimal pseudo-random condition.
I mean, it's also pseudo-random, but not optimally pseudo-random.
So yes, optimally pseudo-random KT3 graphs of the highest possible density have important sort of applications elsewhere as well, apart from these maximum problems.
For K4 free, this is still one of the optimal constructions.
Okay, so now we are going to prove the lower bound. So remember that in the Edwards bound, a proof I left as an exercise actually of the root M bound actually consisted of two lower bounds. The linear lower bound that is constant at least constant times n, and the bound that is at least constant times m over n. So we sort of split into two regimes, one where the graph was fairly dense, one where the graph was fairly sparse, and then we sort of took a combination of these two bounds. The similar approach is very common, and also that's kind of the approach we did for this surplus on KT3 graphs, where I used Ramsey's theorem to prove that the chromatic number has to be fairly small, and we get an improvement on the root M bound. So it's not surprising the similar sort of approach will be used here. So we are going to split into two regimes. One where sort of okay, so through this proof, you can basically ask. I'm going to do it for any graphs. If you want, in your head, think of the proof as in the proof as G being D regular for some D. It's going to simplify some steps, but I kind of want to also show how this can be done in general, because there's one trick that's going to be useful in general, which sort of vanishes when G is not regular. But yes, so it's not surprising that this regime where D is going to be roughly n to the 2/3, or more precisely, D is going to be roughly m to the 2/5, is going to be play a sort of a important role, and that's where our bounds meet. So let's start with our first lemma. So if G is triangle free with degree sequence, D1 up to Dn, then the surplus of G is at least some constant times sum of the square roots of Di's. How I really want you to think about this is if G is D irregular or close to D irregular, more precisely, if it actually works if the max degree of G is upper bounded by some reasonable size constant times the average degree, then the surplus is root D times n, which is what you get for this optimal pseudo-random graphs. So hence, this basically sort of morally allows you to deal with the regime where D is small by this heuristic. So this was first proved by up here, I believe, Shearer, by a very sort of a complicated argument. And then this was used as a black box by Alon, who also proved the lower bound m to the 4/5. But here we're going to give a more recent proof, which uses the Goemans Williamson method, which follows an approach presented by Carlson and others. Again, I advise you to think of the case when G is D regular in this proof if you feel that it's easier. So now suppose that we are in a regime where all these degrees goes to infinity. Like say the irregular graph with D not being constant, but D tending to infinity. We are gonna look at vectors in R to the n, but here we index the coordinates by the vertices of G, which is a trick that I mentioned at the very end of last lecture, so that we give one large coordinate in the direction of u for xu. And then we add a small sort of a noise away from the bth direction if uv is an edge. And here the point is that, remember, we want our inner product to be slightly biased towards negative numbers when there's an edge between u and v. So if I look at xu, xv for uv being an edge, then this is going to contain terms xu, u, xvu plus xvv, xuv, xvv plus something else. And so this guy's 1, this is minus 1 over du, this is minus 1 over dv, and then we have something else. And what this something else is going to be pairs of products of this type. So if there are not too many of them, these are going to be roughly 1 over root d, 1 over root d, and if we are assuming that we are roughly regular, it's going to be minus 1 over root d, minus 1 over root d, terms which are proportional to 1 over d squared. So if there are not too many of them, hopefully these first two dominate, and that provides that this is heavily negative on the edges. So the point is these vectors are kind of roughly orthogonal because we have one very large entry towards the. So think of this as a xu being the used coordinate vector EU plus a little bit of noise away from those which are neighbors.
Is there any other term given that G is triangle free?
Well, exactly that's the point. There are none. But this is for the this intuition works in a bit more general setting, so I was just about to go there soon. But this is sort of why this sort of shows that you fix one for u equals v, and then something else depending on whether you have edges, non-edges. Sometimes you have to deal with large pairs of co-decreases separately. Now we live in an easy case when our graph is triangle free, and we are not gonna have any other terms, but let's not get ahead of ourselves. The point is, even if we don't make that observation yet, and we assume that the graph is regular, we are going to have -2 over root d plus 1 over d times hopefully a small number of terms, so that these two guys dominate, and that ensures that along the edges the inner products are slightly negative. Okay, so let's now actually see there are no other terms. So xu of s is non-zero if and only if s is in the close neighborhood of u. So this is non-zero if and only if s is in the close neighborhood of u intersected with the close neighborhood of v. But because uv is an edge and g is triangle free, it follows that the neighborhoods cannot intersect. So we concluded the only, as pointed out correctly, the only non-zero terms occur when s equals u or s equals v. So its inner product is just 1 over root minus 1 over dv. One crucial feature which we don't have here is that these are not, strictly speaking, unit vectors, a condition I forgot to mention here, which I did, I think, yesterday. But obviously that doesn't matter because we can just scale them to be unit vectors. Here, and also, like, we could also get a variant because we don't care about multiple constants, as long as every one of them has roughly the same norm and has a constant norm.
So why isn't it y over d? I think it's y over square d, root d squared.
Sorry, no, I didn't follow. So here, this inner product is really xu xuv plus xv xuu times xvu, because it sums of this form. So the only non-zero terms are when we plug in s equals u or s equals v. When s equals u, this guy is 1, and this is -1 over root du. 1 over root dv. When s equals v, this guy is -1 over root du, and this guy is 1. So we really get this expression. Okay. So note that the L2 norm of each of these vectors is 1 plus du divided by du. So they have constant norm. And actually they have an equal norm. So we just scale them all by a factor of 1/√2, and then we get unit vectors. So that doesn't change the calculations up to multiple constants. So now if we cheat a little bit and are sloppy and claim that arcsine of x is x and pretend that this is actually some sort of inequality, then we get that the surplus of G is lower bounded by this sum. And now there are du terms, 1/√, du, so we get exactly this sum as our lower bound. And because all of those inner products are actually negative, we could get an inequality of the form arcsine of x is at this alpha x, which holds for all negative real numbers in certain range. So that actually I'm not even cheating with the slower bound. It's a bit more tricky when we live in a situation where in our application, some of the inner products are positive and some of them are negative. There we have to do two bounds, one for the positive inner products and one for the negative inner products, which might have different implied constants. And then we kind of have to hope that, which is pretty much often or always the case in our applications, that as long as none of these inner products is too large by absolute values, then the sum of the positive inner products is small because they are bad for us, and the sum of the negative inner products is large by absolute value, and they are the ones which give us the last surplus. So even if we multiply them by constant which are slightly off, then our application still carries over. Sometimes world is not that nice place, but then you can sort of do some ad hoc tricks to try to get around it, or look at the cubic terms in the Taylor approximation. I should also mention that the reason why I here didn't want to say that, oh, look, the graph is triangle free, so we get rid of some terms. These remaining terms immediately, is that this approach is sort of robust enough that if your graph contains only a few triangles, then you can still get some meaningful out of this, as long as it's close to regular, because then you get rough terms of the form 1/d times the intersection of the neighborhood of u and v over edges. And if you sum those up, that's basically counting the number of triangles you have in your graph. So if your graph is regular and contains a very few triangles, where if you run the numbers, you'll get some sort of idea what this very few means, you can still get some similar type of bounds for the surplus. But there you have to be a little bit careful, I think, because you might run into the troubles if all of your triangles are concentrated on certain edges, because then it could be the case that some of these inner products are, even though in average they are distance don't matter, there might be few edges which are in very like a lot of triangles, so you have to be a bit careful with that. This variant was studied, among other things, by in a paper of Stefan Glock, Oliver Janssen, and Dennis Sudakov. So that's sort of probably the best example of very sort of involved applications of this Goemans-Williamson method when bounding surplus. I'll shortly mean what degenerate means if you don't know it yet. Then we claim that the surplus of G is at least m to the 4 over 5, meaning the balance we want. And this is exactly the sort of threshold we are aiming for, because this is the sort of break point where optimal pseudo-random triangle with free graphs no longer exist. So degenerate means there is the order of the vertices v1 up to vn, so that the degree, the ith degree, d less than I, which we define as the number of j, so that vj, vi is an edge, and j is less than I, is less than d. So there is an order of the vertices, so that each vertex sees at most d neighbors amongst those vertices that preceded in the order. And it's not too hard to see if d is not degenerate, then it means that there's a subgraph with mean degree at least d. Because basically, the easiest way to construct this is to backtrack. You start with your v1 up to vn. Vn has to be a vertex of degree at most d. So you need a vertex of at most d to sort of get around it. And then you keep going. And then if you can't proceed in this greedy way, then it means that you find a subgraph with mean degree d, because at some point you no longer have anything that you could remove. And that's what we're going to use in the other extreme regime. Okay, so the proof is quite easy. So the surplus is all bounded by the sum of the square roots of degrees by the previous lemma. And it certainly don't hurt us if we decrease each of this number. Here we are just replacing each di with d less than I. So we are only considering those neighbors which are before it. But now it's very good, because all of these numbers are at most d. So this is lower bounded by some of them divided by root d. Because here, if you look at each individual ratio, we are dividing by a number that is larger than any of those, so that's totally fine. But this guy is just a number of edges in G. So we are done. Why? Because this is basically counting every edge once, because we are looking at, in this order, the right endpoint of the edge. And usually if you look at the degree sum, it's twice the number of edges, because every edge is counted once for the left endpoint, once for both ends point of the degree sum. In this sum, we are only counting it with respect to this order for the right endpoint. So we get that this equals just the number of edges, not twice the number of edges. And again, an instructive example of the thing is just when these, this is just a technical tool to work with graphs that are not regular. You should think of G being regular, in which case it is just evident from the lemma. And we need to do something along these lines, because think of an example where you have a optimal pseudo-random graph, and then you have a disjoint union of something that is, I don't know, closest to being bipartite and has a large sort of decrease. So it could be that the edge density is controlled by the second bit, but it's good. Sorry. No, I said it's just incorrect way. Well, anyway, basically your graph could be somewhat a disjoint union of two very well behaved, very differently behaved things. So you can't sort of hope to find sort of a find a very well-behaved argument that works for every irregular cross, but this is kind of like you keep throwing away some large degree vertices because you know that either the large degree vertices kind of don't affect the overall edge sum that much because there are not too many of them, or you actually can't throw them away without making a large a subgraph with large min degree, in which case this type of approach is always going to fail because your edge density over there would be much larger than what you would expect in an optimally triangle, pseudo-random triangle free graph. So as said, if G is not degenerate, then it contains an induced subgraph with a large min degree. So this is the sort of the other case we have to consider in top of the previous lemma. But here we can't assume that it's the whole graph G, which has a large min degree, but rather some small subgraph. So here I'm using a fact that if G has a subgraph H with induced subgraph H with a large surplus, then the surplus of G has to be large. And I'll leave it as an exercise. In fact, if H1 up to Ht are vertex disjoint induced subgraph of G, then the surplus of G is lower bounded by the sum of the surpluses of H i's. For graphs, this is not necessarily that useful of a statement, but surplus and cut problems exist for hypergraph as well. And there this is actually a pretty convenient tool because that allows you to, I think I won't have time to talk about the hypergraphs during this course, but there you can sort of get rid of high co-degree vertices using this method. But here we just need the variant where the surplus of a graph is lower bounded by the surplus of any of the induced subgraph G, and hence this argument gives us the desired problem. Okay, so the rough outline of this argument is as follows. We want to prove that H has a large surplus. And H has a large min degree. So one way to prove this is H has small chromatic number. Not quite true in general, but again using this trick, maybe we can prove that H has a large induced subgraph with many edges and small chromatic number. Because then if you pass this H double prime, which still has many edges and small chromatic number, sorry, maybe I said large chromatic number, but I meant small chromatic number, then the surplus of H is again lower bounded by the surplus of H prime. And because it has many edges and small chromatic number, it is a large surplus. So, and here we use the triangle free but in a rather neat way, which is the following. Suppose we have a dominating set, which means that everything here sees at least one neighbor of size R. Everything here sees at least one neighbor in this dominating set. Then we can actually come up with a proper vertex coloring by declaring the color of this vertex to be I if it sees the if it's connected to the ith vertex here. Because if two of these things were both colored with I, it means that both of them have the vertex vi as the neighbor, but that gives you a triangle. So basically, what we want to prove that H contains a rather small set which dominates a lot of vertices. Yes?
Sorry, I'm a bit confused. Like, so what is the relation between the previous lemma and because I think like by delta H is greater than or equal to m to the 2/5, it seems like in the language of the previous lemma, it says that H is not degenerate. But
Yes.
but then you are going to prove the same thing. Like,
No, here I assume that G is degenerate.
so
So it means that there is ordering of vertices, so that
yeah,
this is always less than D.
so I'm a bit confused because if G is degenerate, then surplus G is lower bounded by
Yes.
4/5. And
If it's not degenerate, then this condition holds. Because if this condition holds, you can't like basically if it's not degenerate, then whatever order of the vertices you get stuck at some point, which means that basically once you have removed some vertices, you can no longer find a vertex with min degree at least D, which means that you get an induced subgraph with large min degree. So if it's not degenerate, then there's an induced
then
subgraph.
there is another argument to show that this is still lower bounded by m.
Yes.
Okay.
So these two cover all the possible graphs.
Right. So there you also have the triangle free assumption.
Yeah, sorry. I mean, like, I'm trying to bound the surface for the triangle with free graph, so if I ever forget to add the assumption that G is triangle free, then please shout at me. Because, yeah, sure, but like, this bound doesn't hold in general, so, and we are trying to prove it for the triangle with free graph, so yes, G should always be triangle free. So, so now the question is that if our graph has large min, if our subgraph has large min degree, does it mean that there is a small dominating set? In Alon Spencer, one of the first applications of the probabilistic method is to prove that you can find a small dominating set, basically that dominates quite a large proportion of vertices, and then you add the rest into the mix. Here, we don't really care about finding a dominating set for whole of H, so we can just pick a random set, look at what are the vertices it dominates. As long as that set is large and contains many edges, that's good enough for us, because we only care about finding a sort of a large integer subgraph, so we can just ignore the leftover vertices which are not dominated by this random set, if we want. So this is kind of the rough overview. What motivates the proof? I'm just going to write down, because the proof, if you just read it as it is, might look like it's coming out of nowhere, but actually there is a very sort of natural reason behind it. So we fix the parameter R to be 2 times the size of H divided by D. I in general hate putting floral cereals, but I guess here this might be a rather small number, so let's put it for safety. And we pick our vertices from the vertices of H uniformly at random. And allowing repetitions. So we get the set R with vertices V1 to VR, and we allow this set to be a multiset.
What if H prime?
Sorry, H. Yeah. And let H prime be the index subgraph, which consists of those W in V of H, so that W also belongs to the neighborhood of R. So it's dominated by R. So now what's the probability that W belongs to H prime? Well,
Sorry, is that close neighborhood of R?
here I really want this. Actually, that's a good question. So if there are H's inside R, I can take those VIs which are there. But if, say, one of the VIs is not joined to any other VJ, then I won't leave those aside. In principle, I don't think it makes big difference. But in this way, I believe nothing goes wrong and all the estimates are still going to be true. So probably that W is not in H prime is obviously at most 1 minus D divided by the size of H prime, because every one of these VIs have D neighbors, because mean decrease D, and the probability that W is not a neighbor of VI is this. These are chosen independently, so the probability that W is not joined to any of them is at most this. And this is at most e to the minus 2, which is at most some number. All we care about that this is less than 2. Because then for all W1 and W2, the probability that W1 and W2 are in H prime is at least 1 minus quarter minus a quarter, which is half by union bound. And in particular, we want this to be a strictly positive number, because then this implies that the expected number of edges is still large.
Sorry, should that be D over the size of H instead of?
Yes, size of H. Thank you. So the point is, we want H prime to have roughly the same number of edges as H up to constant factors. And now we'll just prove that H prime has low chromatic number. So let chi be a function from the vertices of H prime to R, so that chi of W is the smallest integer I, so VIW is an H. And for such I to exist, we need W to be neighbor of at least one of those VIs, but that's satisfied by the definition of H prime. So this is a non-empty set, so it has a minimum. And if there exists an edge such that both of them receive the same color, and let's say it's J, then it just means that W1 and W2 are connected, but they are also connected to VJ is a triangle in G, and this construction. the chromatic number is less than R. So the surplus is at least the number of edges in H prime, and remember that R was H over D up to constant, so and because so here we fix an instance of R so that the number of edges in H prime is at least the expected number of edges. And this is just of the order D squared because the min degree H is at least D. So the number of edges in H is at least half times D times the size of H. And by just D, this gives us the correct exponent for the surplus.
Sorry, I'm a bit confused. Why does it imply that the chromatic number of H prime is at most R?
Because this is a proper Vertex coloring. Because if there were an edge for which both of its endpoints receive the same color, then these guys would form a triangle.
Okay.
By our construction of the set of VIs. Okay, so let's have a quick break of 5 minutes. If you have any questions, you can ask them during the break, and then we continue. I might have used D in the previous proof, where D was just M2 over 5, as it was in the proof of the other regime. So if you were confused by that, I'm sorry. Secondly, so I'll do this quite quickly. So for the positive discrepancy, we can also get an estimate by using the Goemans Williamson method. So here we just do the same trick. So we pick W uniformly at random on the sphere, and we let U to be the set who chosen so that we choose all the U's for which X, U, and V have non-negative inner product. So now the expression for the lower bound is a little bit more complicated, but the proof follows very similarly. Remember, basically the probability of whether they are in the same part or a different part can be expressed by using the angle between the two vectors, and the angle between them is argus cosine of the inner product. So this is roughly speaking or actually it's exactly the probability that they belong to the same part of the cut. Actually, I think I want here factor 2 those. But anyway, it's a constant factor. And then for the U choose 2, just to sort of make sure we are on the same page, which is right. So think of U as a random set, then the size of U times U minus 1 can be written as the sum over all the distinct U and V's of the integrated function that both of them are contained in U. And then you just, this is literally the linearity of expectation argument all over again.
Sorry, that is D over what? D over 2 times.
D over 2 times n minus 1. So that's basically coming from the to be more concise, let's just put a P over 2 here. because here I have written down that you choose to sort of as u times u minus 1 and pulled out the factor half in front. So to be more consistent, let's put a p here. The previous one might be off by some lower return. But yeah, I'm summing over all the pairs, so every pair is summed twice. So that's why I bring the factor of 1/2 in front. And we are going to be again sloppy. And we are going to sort of we are going to think of this as if positive discrepancy being lower bounded by let's just put a constant factor here. Won't be the inverse. And now it's even more trickier than in the surplus case, because here we have two terms. So here we have a sum which kind of like positive coefficient in front, and here we have a negative coefficient in front. Here, if you want to do things precisely, we have to be really careful that we properly use sort of lower and upper bounds in both positive and negative ranges. So here, what I'm saying is that this is actually not, this is far away from being rigorous anymore. It's still a good intuition, and you can make the details work in most of the cases, but you like when writing it on proofs, actually you shouldn't do this. But because I want to give you an intuition how this what's more of that, like I think it's more important to learn how to choose these vectors and how in general these methods are applied rather than how to work out these tedious estimates in practice. That you can, if you're really interested, you can actually learn by reading the papers rather than, but here the point is to give an intuition how these things work.
So you claim that this is, although this is not the Taylor's expansion, but this still works pretty well in the applications. If you replace this arc cosine just with arc cosine.
Yes, so basically the thing is that you're right. Arc cosine, you have to worry about a little bit with the constant terms, but the constant terms will actually cancel because of you're summing over m over 2. I mean, the sum of the constant terms is going to be m in the first sum, and it's going to be also m in the second sum because you're weighting it by p over 2, and p over 2 times n minus 1 is just m. So the constant terms will cancel, and what you will get.
But there's no square, just this inner term.
Yeah. You're right.
Sine. Okay, sine. Oh.
I think I've maybe screwed up, so maybe there should be some. I'll double check it for tomorrow. It's probably some calculations incorrectly, but basically, I think this probably should be. Yeah, I think it's actually pi over 2 minus arc cosine of. That sounds more like. Yes, because the probability for being in a cut is twice the arc cosine, so I think this probably what's correct. Yes, thank you. But here again, we have some constant terms here, and they will cancel out. So basically, what you and then we should minus over here as well. So what you get is basically the arc cosines being the leading terms with correct constants. And for our purposes, we think of this as the correct thing.
I get
And tomorrow I'll give another sort of reason why this is not too bad of an approximation, where we completely get away from the rounding errors.
the constant term is itself summed up if the constant term times this plus of G.
Sorry?
I guess the constant term itself gives this constant plus this capacity times some constant term.
No, so actually here the constant terms will cancel out. Because here we are summing over all the edges, and here we are summing over all the pairs. But because this is the edge density, so here we have m of the same constant term, and here we have p times n plus m minus 1 over 2 of the same constant term, but that's just m. So they will cancel. So what we really are at with the other arcsigns. But this is sort of the variant that you should think of it. And that kind of makes sense, because here, now what we want is we want the inner products to favor positive numbers along the edges, or more precisely, the second term is just the sum of the inner products. And we would like there to be more positive weight along the edges than on average, which is the same as saying the edges should be sort of contained more likely in the same random half sphere we choose. Because by linearity of expectation, like our argument is Ru is going to be all the vectors that are contained in a random half sphere. That is more likely to happen. Like a pair of vectors is more likely to be contained in a random half sphere if their inner product is positive, rather than if it's negative, because that means they are like more towards antipodal than in the same half sphere. So that means if we want there to be many edges in our random set U, then the inner products along the edges should be larger compared to the average, which motivates why here we have a positive coefficient instead of the sum in front of the sum of the inner products over the edges. Whereas in the maxgraph we had minus sign in front of the sum, because we wanted really to sort of make sure that edges went over the cut from one side to the other. Okay, so the first theorem is that if d is between 1 and 2/3, then the positive discrepancy goes out to this right through d times n. And this is typed for G and P, with P being roughly d over n. When d is larger than 2/3, we no longer can prove this lower bound with this method, but we can prove another lower bound, which beats the linear lower bound as long as d is sublinear. For d being constant times n, this still gives a linear lower bound, which is not too great. But this is a result of Benny Sudakov, Isam Toman, and I, which was published this year, or will be published this year, but the preprint came out 2023. I should point out that Alon proved this when d is at most n to 1/9 and g is regular. Our approach works for average degree, although when proving this, I will only show it for regular graphs because the proof is a bit simpler for regular graphs. And what's actually quite surprising is that this is typed for in this range. For the reason that there's a strongly regular graph with d roughly n to 3/4 that matches this bound, and then we can just take a randomly induced subgraph of it of appropriate size. and the scaling works nicely enough that this gives us positive discrepancy of the n squared in this range. So this means that something very weird happens for the positive discrepancy, because if you think about it as a function, like how large is the positive discrepancy divided by n, which is sort of the natural thing to look at because it's how much it beats a linear lower bound. And here I have how d grows. So this means that up to a certain point, this grows linearly in d because it's like, so let's say that this is n to the alpha, and here we are plotting the alpha, and here d is n to the beta, and we are plotting beta. So this corresponds to the curve alpha equals half beta, because, well, positive discrepancy of g divided by n, in the worst case, is lower bounded by root d, by this theorem, and we know that this is tight.
So just to make sure that Alon proved a lower bound, right? Yes.
Yes.
Not an upper bound, right?
Well, I mean, the upper bound is tight because it's tight for GNP. So, sorry, the upper bound is not interesting because it's tight for GNP.
Oh, sorry, you wrote that Alon's result is a big O or big omega?
Big O.
Big.
So when D is small, much smaller than this here.
I see.
So this is much earlier result. It's from 1991. So I'm just mentioning as a historical background that it's not the first result in this direction, but it was also like Alon proved similar things for much sparser graphs. And assuming they are regular, by very different type of methods. So he sort of considers very specific edges very far away and proved
And the new result does not require regularity.
it doesn't require regularity, although the proof I'm going to give here works only for roughly regular graphs, but and for simplicity, I'll show it only for regular graphs. It's one of those proofs which is quite common in this area, that you basically have a proof for the regular case, which is rigid enough to cover the regime when the max degree is bounded above by constant times the average degree. And then if the max degree is not bounded by constant average degree, then either you can delete all the vertices which have a large degree, and that doesn't contribute to too many edges, and you can apply this type of result on the remaining graph, and adding back the deleted vertices doesn't really change the game. Or they are incident to many edges, and then that fact on its own already gives, by some ad hoc methods, a large positive discrepancy. But this is sort of the, I would say, the interesting regime, and the sort of getting from regular or near regular to the irregular case is sort of more of like tedious technicalities, which is not that interesting. But the point was that if we look at the sort of worst case scenario, so how small can the positive discrepancy be? Then here we have this linear growth because we have the lower bound and we know this is tight for random graphs. But here we start dropping because we have this n squared over d, the lower bound, and it's also tight up to and 3/4. Now, technically our lower bound is still dropping. Tomorrow we'll see that there's a lower bound which starts increasing again. Sorry, not quite over here, but somewhere over here at n over 4 over 5. And then obviously at d equals half minus epsilon n, it drops to 0 because we have a complete bipartite graph. So it's sort of not at all monotonous function, or not at all, it goes up and then it drops at the complete bipartite graph, but it goes up, then it goes down, then at some point, which we quite don't know, it starts going up again and it drops down. I mean, it could be that the behavior is very wild in this regime that we don't know. We don't really understand yet, but it's really saying that the behavior is pretty wild. So not surprisingly, actually in both cases, we pick XUV to be 1 if U is V, alpha if UV is an edge, and 0 otherwise. Just as we did last time. And here we want alpha to be less than 1 over root D. And here we are assuming G is D regular. Just to ensure that our vectors have roughly unit norm. So if alpha is less than 1 over root D, then they have L2 norm at least 1 and at most 2. And they also have, because we're in this regular case, they all have the same L2 norm. So when we scale them down, we are only going to lose some constant factors. And I'm running out of time, so I'll just say that in the first regime, you choose alpha to be C over root D, where C is a small constant. And in the second regime, you choose alpha to be C times N over yes. So we have the lower bound for the positive discriminant, we can write it down as it's at least so it's at least a lower bounded by constant times this sum minus constant times that sum. So we want to basically ensure that this is large and this is not so large. And I'll just steal maybe 2 more minutes to roughly outline why this is going to be enough. So, well, if UV is an edge, I think I made some slip here, so I want 1 must be here. That's because in the second sum I actually have 2 terms for each edge. And where did I state the theorem? I think I said D less than N over 2. So here we are really using the fact that this 1 minus P is at least some constant greater than 1, so we are not in a very dense regime. I mean, it's not really, this bound is not anyway super interesting when D is linear in N because it matches the constant times N lower bound anyway. So if UV is an edge, then the inner product of XU and XV is 2 times alpha. So we have a contribution 1 times alpha from the XUU, XVU, and another from XUV, XVV. And then we have alpha squared times the side of the joint neighbors. But I don't really care about this. It's at least 2 alpha. On the other hand, if UV is not an edge, then we only get this contribution of the second term. And this sum is at most alpha squared times N times D squared. Why? Because each W contributes to at most d times d minus 1 such terms. Because the w contributes to such term if and only if u and v are both in the neighborhood of w, but because we are working with the irregular graphs, the number of such u and v is d times d minus 1. Because we have to choose two different elements from the neighborhood. You can see that this is an estimate that can go terribly wrong if the max degree is very high. And in general here, we could just replace d with the max degree. And if our max degree is bounded above by constant times the average degree, then things don't go too much sideways. But from here, we sort of get that the sum over the edges of these inner products is at least 2 times alpha times n times d. So let me just write it without constant multiples. So basically, the positive discrepancy is lower bounded by a positive term that is proportional to alpha and d, but then we have to subtract a term which is alpha and d squared times p, which is roughly n over d. So this is subtracted p. And we want to choose alpha so that alpha is less than 1 over root d, or constant root d, because that's what we need from the fact that these are this can be scaled to be unit vectors by divided by constant. If we divide by something that grows with n, then we are in trouble, because then we would actually have to divide by this whole expression by this the sort of roughly the L2 nodes, which would actually not just affect the constant multiples. But then we have this competing term, which can be pretty bad if d is large, because this is d cubed. So basically, this means that the best we can do we must choose alpha so that this first term dominates the second term, but so that, and preferably alpha as large as possible. So what we just get is we choose alpha to be constant divided by root d for as long as we can, and it turns out that we hit the barrier when d is roughly n to the 2/3. And at that point, we get a condition. Basically, we ask when is this function roughly that function, and that happens exactly when alpha is n over d squared. And that conveniently is less than 1 over root d when d is greater than n to the 2/3. So that's a legal choice up to a small constant. And in that case, as long as we choose alpha to be small enough constant times n over d squared, here we have here we are linear in the small constants, here we are quadratic, so we can ensure that the second term, while they have the same magnitude, maybe the second term is smaller. I encourage to do the actual calculations by yourself to get used to this, but I'll stop here. And tomorrow we see some nice applications of these results for second largest eigenvalue, some different arguments for the second largest eigenvalue, and hopefully at the rest of the regime, what happens for the positive discrepancy when d is roughly linear, but smaller than half n.